Let us now move on to the next type of dependent processes, which are martingales. Now, before we dive into the definition, let us first clarify here this notation concerning the increasing sequence of sigma fields that is popping up in the definition. Now, when a random sequence is generated, the current member, let's say xt, is determined in an environment in which previous members are given. So in short, the past is known and the future is unknown. And the operation where we conditionally sequence on past events is often of crucial importance when we establish results in our time series context. Now, how do we characterize this accumulation of knowledge by an observer as time passes? Well, by specifying an increasing sequence of sigma fields. You can actually loosely interpret this as an observer's information set, which gradually expands as time passes on. Now, if a stochastic process is Ft measurable, then it is said to be adapted to the process, where an adapted process is one that cannot look into the future. So let us now return back to the definition of the martingale. Our stochastic process is a martingale with respect to this filtration if it satisfies these three conditions. It needs to be adapted, of course, to the filtration. Its first absolute moment needs to be finite, and the conditional expected value of x is equal to xt minus 1. Now, an interesting special case is a so-called martingale difference sequence, where all of the conditions are the same except for the last one, where the conditional expected value should be equal to 0. Now, we've seen this conditional expected value popping up already before, namely in the definition of the optimal forecast in the session on VAR models. Knowing what we've said there, we can then also conclude that the best one step ahead prediction for this error process is 0. Now, since I use this epsilon notation over here for a martingale difference sequence, it will be no surprise that this is actually a process that we can make use of for the error terms in our model. And then these two questions you might ask yourself, namely, how is the MDS, so the martingale difference sequence condition, related to independence and serial uncorrelatedness? Well, the MDS condition is stronger than serial uncorrelatedness, since a serially uncorrelated sequence cannot be forecasted on the basis of a linear function of past values. But in contrast, no function of past values can forecast an MDS. The MDS assumption is, however, weaker than independence because it does not rule out the possibility that, for instance, higher moments might depend on the past. Now, there also exists a central limit theorem for martingale difference sequences, which I summarized here on the slide. But actually today, we won't go over this in detail, but I already put it here because we will make use of it in one of the upcoming tutorials. Lastly, I also still want to have a look at mixing processes. So just like M-dependence was a natural generalization of independence, well, mixing is also a natural generalization of M-dependence. And there exist various mixing concepts in the literature, which are all based on some measure of dependence. Now, to get some intuition, let's first suppose that we have two independent events, let's say A and B. What do we know then about the difference between these two probabilities? Well, for independent events, you should know that both are equal to each other. So this difference, why do I put it here on the slide? Well, because this difference will pop up in various definitions of mixing processes. For instance, for alpha mixing. For alpha mixing, we are looking at two sets of possible events. One where we look up to and including the time point t, and one that looks at events starting only at time point t. Now, an intuitive measure of dependence between all events that are separated by, let's say, L time units can be given by this formulation, where we also see the same difference of probabilities popping up between our two events, namely the event A that belongs to this first set and the event B that belongs to the second set, whose starting points is L periods after the ending point of the last one over here. And to arrive at a single measure, we will still take the supremum over all such possible events. Now, of course, in this definition, we still have the dependence on t. So we can cancel that one out by taking yet another supremum over all time points. Now, how is alpha mixing then defined? Well, a stochastic process is said to be alpha mixing if asymptotically distant events. So when we let L go to infinity, well, when these events are independent. So when this measure of dependence over here goes to 0. Now, we've seen n-dependent processes before, and they are alpha mixing, since the dependence measure is 0 for all values of L larger than n. Similarly, stationary invertible ARMA processes are also alpha mixing. But note that the conditions are very difficult to verify theoretically and actually impossible to verify empirically. So we won't make further use of these dependent processes in our course, but note that law of large numbers and central limit theorem do exist for mixing processes. The last part that I still want to address in this video concerns the extension of our results from the scalar to the vector case. And remember that I started these slides over here with a very simple regression model, and that we arrived at this key expression. Now, we've seen that the law of large numbers and central limit theorem are available for dependent processes, but until now, we only dealt with the scalar case. But now, we need to deal here with vectors and matrices. So what will happen for the first term? For the first term that I copy over here, well, for that guy, it's rather easy. Since a sequence of random matrices CT converges in probability to a matrix C, if just simply each element of CT converges to the corresponding element in C. So we can just establish convergence of a matrix by looking at its individual elements. That's nice. What about the second term in our key expression, which we need for the central limit theorem? Well, a very powerful device here is the so-called Cramer-Bolt device. And this theorem says that a random vector sequence converges in distribution to a random vector y if and only if this linear combination of the first guy converges in distribution to the same linear combination of y. And this for every fixed non-zero vector alpha. Okay, so why is this theorem so useful? Well, the relevant part in the statement is this if and only if expression, which means that if we can show that this linear combination converges to that linear combination for every alpha, well, then we get the distributional convergence for the vector for free through the Kramer-Wold theorem. And why is this so interesting? Well, this is interesting because the terms that are involved here in this expression are scalars. And that means that the central limit theorem results for univariate cases can be used to show the results for a vector, a multivariate case. And that is really especially nice since there are many CLT results available for scalar sequences, which we can make use of. Okay, so to summarize things, to look into the asymptotic distribution of beta hat, we first need to arrive at this important key expression, and we will then use the weak law of large number on every element, so element-wise on the first term, to derive its probability limit. And then the Kramer-Wold device will ensure that we can establish the joint convergence of the second term, making use of the central limit results that are available for scalars.